Welcome. In this video, we're going to continue our discussion of solid-state physics, and we are making way into understanding how semiconductors work in order to appreciate their function in detectors, X-ray detectors. So last time, we introduced the idea of metals and how metals bond. And in particular, we noticed that our current description of metals is best captured by the idea of free electron theory. That is, whenever you have a large sample of a particular metal, all the electrons of those atoms don't have a sense of belonging to any particular atom, but they belong to the entire sample. And because of this, the electrons can be viewed as a gas that is all the time in motion. That is why, or this is how we accounted for why metals are typically good conductors, because they have all these electrons not particularly tied down to any atom, but free to roam about. Hence, they could carry electricity, or they could convey electrical charge from one point to the other. So this is how we accounted for metals being good conductors. But then, of course, we knew that because they behave like gases, and we knew that gases, whenever you increase their temperature, they're going to move faster. This means the warmer or the higher the temperature of a metal, the more of a good conductor the metal is going to be, because that means the higher the temperature, the higher the kinetic energy, hence the faster this gas of electrons is going to move. This idea is very, very useful. However, it still lacks some of the distinctions we observe, that not all metals are good conductors. So how can we account for this, that not all metals are good conductors? Some metals, they are not necessarily good conductors. Although this helps us to understand why good conductors can conduct electricity, it doesn't help us to know why some metals are insulators, others conductors, and others semiconductors. The point is, we need to improve our idea. Well, one of the things that this model of free electrons overlooks, or one of the assumptions, is that the electrons that are roaming around as an ideal gas are assumed to not interact with one another. And that is not necessarily true, because we know that electrons will interact with one another, and there will be some kind of a potential, and because they're going to interact with one another and there's going to be a change in potential, there's going to be some kind of a force. So they're going to affect one another. So how can we improve on this theory? Well, before we get there, we need to again go back to the basic principles, that although these electrons are moving around and they don't belong to any particular atom, they still must obey Pauli's exclusion principle. And Pauli's exclusion principle states that no two electrons of an atom or of a sample of some material can have the exact same quantum state. They have to differ in one way or another. If they're on the same energy level, they have to differ in the other parameters, the other quantum numbers. And one of the easiest ways, helpful ways, visual ways of showing this kind of a distinction, that electrons should not have the exact same quantum state, is to use this diagram called the electron configuration diagram. So for instance, in the first orbit, that is the 1 orbit where n is equals to 1, the maximum number of electrons that can be housed or can be accommodated there is 2. Since we can only have two electrons. Although they will be on the same energy level, they have to have different spins. That is why we draw one electron up and one down. These two arrows are to show us that although these two electrons, represented by the arrows, have this same energy, belong to the same energy level, they have different spins. So although both live in n equals 1 energy level, or in the shell n equals 1, but their spin distinguishes them from one another. And the same is true for the second orbit. That is, we're going to have one up and one down. And if we had more electrons, we would put them on this suborbital of the n equals 2 shell. And the way we would populate this, again, would be one spin up, one spin down. It would be one spin up, one spin down, one spin up, one spin down, one spin up, and one spin down. That's how we would populate this. Again, Pauli's exclusion principle cannot be violated. Okay. However, before we improve on this method, it's worthwhile for us to review and use an example. When we considered the hydrogen atom, we said certain regions from the nuclei were allowed. In other words, certain radii from the nucleus were allowed for electrons to orbit at. The first allowed orbit was this one, which we called n equals 1. And the second one was over here, we called n equals 2. The third one was n equals 3 over there. And the empty space in between these allowed regions where electrons can orbit, these were forbidden. Electrons could not reside here. They had to reside exactly at this particular radius, or that, or that. They could not reside anywhere in between. These were forbidden regions. Only these specific radii were allowed. Another way of representing this is using the energy diagram this way. That is, that energy level was allowed, and that one was also allowed, that one was allowed. These were the permitted energies that electrons could have, but anything in between, that was forbidden. That was forbidden. Now, this is true for when we're dealing with one electron, and it's one hydrogen atom. And it's very clear when we're dealing with one hydrogen atom that these regions, obviously, when we have one electron, like for instance, hydrogen has only one electron, hence its energy state is going to be one electron in the first energy orbit. The question is, what happens when you take two hydrogen atoms of the same kind? The electron in the one hydrogen atom is going to be in the first orbit. And the same is going to be true for the second hydrogen atom. But then what happens when you put these two hydrogen atoms together? Well, what happens is, as you bring these two hydrogen atoms together, notice if this was in the spin up, if this electron was in the spin up state when this hydrogen atom was alone, and this one was also in the spin up state when this hydrogen atom was alone, as you bring them together, what's going to happen? Well, over here we had two allowed regions or two allowed states. It was either going to be spin up or spin down in the first orbit, and the same is true here, spin up and spin down. But when you bring these two together, notice now you're going to have a spin up and a spin down from this atom, and a spin up and a spin down from this atom. So when these two hydrogen atoms are bonded, you no longer have two allowed energy states. Actually, now that becomes 4 because you have 2 allowed from this atom and 2 allowed from this atom. So when they bond together, suddenly you're going to have, in the first energy level, you're going to have 4 allowed energy states. Or 4, you can now house 4 electrons in the first energy level. What happens if you take this further from 2 electrons or 2 hydrogen atoms? You have a sample of more than 2. Let's say you have 4 hydrogen atoms. Again, what's happening here is that what used to be one discrete energy level is now become 2 discrete energy levels, and both of these are 1. They correspond to the orbit, the first energy orbit. But this is no longer of the atom, but this is for the molecule. It's quite important that this region here corresponds to a molecule. This side corresponds to a single atom. For a single atom, the allowed region is only 1 discrete energy level. But when you bond atoms together, what happens is that the region is no longer just 1 discrete, but you're going to have this kind of what looks like a split. Maybe this might be a misdirection when I say split, but all it means is that because you're bringing in 2 hydrogen atoms, each of which had a discrete energy level, but when you bring them together, those energy levels are going to they're going to be different because, again, of Pauli's exclusion principle. These 2 cannot be the same, so they have to be different, and that's why we have this kind of what looks like a split. And if you go from 2 hydrogen atoms, you include more. Let's say you have 4. You expect for there to be a 4-way split from just 1. When the 4 hydrogen atoms were individual, they each had 1 allowed region for the first energy orbit. But when you bring them together into a molecule or some sample, then suddenly these 4 regions are allowed for the first energy orbit. And that means there's going to be 2 states for this split, 2 states for that split, 2 states for that split, and 2 states for that split. So suddenly, this molecule in the first energy orbit now can house more than 2 electrons. Actually, it's going to house 2 n squared times the number of hydrogen atoms, which in this case is 4 because we're dealing with 4 of them. And n is equals to 1 here. So this will be the total number of electrons that can be housed in the first energy orbit for a molecule which has 4 hydrogen atoms. I know that's a mouthful, but because it's on tape, you're welcome to review it. Now, what if we had more than just 4 hydrogen atoms? Let's suppose we had 10 or 10 to the 23 number of hydrogen atoms in this one sample. Well, you might imagine that there's going to be a lot more lines here at this for this molecule. Actually, there's going to be so many lines. This region is going to be so dense with these energy states, it's going to eventually look like a band. It will no longer look like individual lines, but there's going to be so many lines, eventually this region is going to look continuous. It's going to look like a continuum. And this is exactly what this slide is meant to indicate. That when you have an n number, an n here is a big number, imagine 10 to the 23, that when we go from a single atom to a molecule that has bonded with n number of hydrogen atoms, in the first energy orbit, suddenly we were going to have this region which can accommodate electrons. And the number of electrons it's going to accommodate is going to be uppercase N. That is the number of hydrogen atoms involved in this molecule, times 2n squared. And because this is the first energy orbit, n is equals to 1, so we're going to have that many electrons which can be housed here. And essentially, this kind of idea is what we call the band theory of metals. This is a very useful way of understanding and distinguishing certain metals from others. It has to do with their energy bands. The key again is that when we go from the atom, the energy goes from being just one level, but it goes to being an energy band. We no longer have one allowed energy level, but we have a region which we call an energy band, which is allowed. So let's contrast this. Initially, we had one radii or radius from which electrons could orbit when they were in the first energy level, second energy level, third energy level, fourth energy level. That radius is indicated by just one horizontal line. That's what the atom side, this is the atom side to the left. This corresponds to an atom. Electrons could only live on these horizontal lines, but could not live in this empty region here. They had to be either on this horizontal line, or they couldn't be anywhere else. However, when we take atoms and put them together into a molecule, these individual lines, they cease to be individual lines. They become a band. Suddenly, this is now a region where electrons can reside. So the first energy level goes from being one horizontal line to being a band, a region. The same is true for the second energy level and its suborbital. And now the regions which were forbidden here in the atom side, in the molecule side, we call these regions, these forbidden regions, we call them band gaps or energy gaps. Electrons are allowed to live here, but they are forbidden to live here. They can live in this shaded region, that's an energy band, but they are forbidden to live in this region because that's a band gap. It's the gap between allowed regions. Okay. Now, band gaps are the regions that separate allowed energy bands. Again, these are allowed energy bands, the shaded regions, and the white regions are the forbidden ones. These regions are the forbidden ones, and we call them band gaps. And a valence band, which is something which will be very useful, it is the energy band, the highest filled energy band. I'll give an example later on. For now, just remember that a valence band is the highest filled energy band, and if you're interested in the theoretical understanding of it, it's the band that's closest to the Fermi level. This might not make sense, but for the sake of completeness, I've included it. And then the other very important region is called the conduction band. The conduction band is the band or the energy band that is available, the one after the valence band. It's the next available energy band after the valence band. So what does this look like? Well, consider this case, for instance. Over here we have a region that is filled. This region, the shaded region, corresponds to a filled energy band. And Eg corresponds to an energy gap or a band gap. Over here electrons can reside, and over here electrons can reside, but in this middle region they are forbidden. Now this region here is filled with electrons. As you can see, this is the lower part, this is the upper part, and it's shaded all the way to the top. Now, because this is the highest filled energy band, we call it the valence band. Anything above the valence band is called the conduction band. Now, if our conduction band is completely empty, this causes this substance, which has a completely empty conduction band, to not be good at conducting electricity, because there are no electrons available to conduct that electricity. Okay. Now, if our conduction band is partly filled, that kind of material which has a conduction band which has some electrons but is not completely filled, it makes that kind of material a good conductor. Over here is a depiction of such a case, where this band over here is the conduction band, and notice this is its lower limit, this is its upper limit. Part of it is filled with electrons, but part of it is empty. What this means is these electrons have room to move. In other words, they are empty states which can be occupied. When you apply an electric field, these electrons can be motivated to move. They're not tightly bound together. Okay, so this is what makes a good conductor. It's a substance or a material which has a conduction band that has electrons, but it's not completely filled. That is very important. On the other hand, we have an insulator. An insulator can have a conduction band, but this conduction band is very deficit. It's short of electrons. There are no electrons to move. And the closest available electrons are separated by an energy gap. In other words, for us to conduct electricity using this type of material, we first have to get the electrons from the valence band to the conduction band, and then this substance can begin to conduct. But typically, insulators will have a conduction band that's empty together with a large band gap. The larger this band gap, the more insulative a material is going to be. And then we have another kind of material known as the semiconductor. I did mention it earlier in the previous video that a semiconductor possesses insulator properties which can become conductor properties provided that the conditions are right. The reason why semiconductors behave this way is because their conduction band is also short of electrons, typically empty, actually empty, has no electrons, but their band gap, the separation between the valence band and the conduction band, is very small. Which means when you supply a certain amount of energy, some of the electrons from the valence band can make the jump to the conduction band, in which case, therefore, this substance will conduct. But again, you need to provide some energy for these electrons on the valence band to move over. Unless there's the necessary conditions for the electrons in the valence band to make a jump to the conduction band, this substance will behave as though it were an insulator. But when the conditions are right, this substance will behave as though it were a conductor. Hence, we call it a semiconductor. Okay, I think this should be helpful in making a distinction. And this is where the benefit of the band theory of metals is helpful. From this perspective, we can immediately see why some metals are good conductors, others they are insulators, and others seem to behave like semiconductors. This theory of bands is clear in describing the different behaviors of these metals. So in short, a conductor is a material with a partly or partially filled conduction band. So the point is, a conductor will have a conduction band that is some electrons, but also has room for the electrons to move or to acquire a different state. And then an insulator is a material which has a filled conduction band. Actually, this is a filled valence band. That should be a valence band. Valence band and an empty conduction band. There's a bit of a typo here, but I'll fix it when I post these notes. But the point is, an insulator, the conduction band is also empty. In addition to an empty conduction band, there is a large band gap. So again, for electrons, you have a filled valence band, an empty conduction band, together with a large band gap. In order for this guy to conduct, we first have to promote electrons from the valence to the conduction band, but the gap is quite large. So this guy is very unwilling to conduct electricity. Okay, and then finally, a semiconductor will behave like an insulator, but it has a small band gap. And when the necessary conditions are met, this semiconductor will behave as a conductor. This substance, this material, although initially it is insulator-like, when the conditions are right, it will behave, it will take on conductor properties. Wonderful. Now, in order for us to appreciate semiconductors, it is useful to review the periodic table of elements. This is essentially from chemistry. What I would like to draw your attention to are these columns: first, second, third, fourth, fifth, sixth, seventh, and eighth. We will put aside for now this middle part. These are typically called the transition metals, this middle part. These columns actually correspond to groups. Typically, this is called group 1, this is group 2, this is group 3, this column. All the elements in that column are in group 3, and these ones in this column are group 4, this one 5, 6, 7, and 8. There are interesting facts in the arrangement of the periodic table. And this is going to be helpful to us in understanding how semiconductors are produced. So, few interesting facts about the elements as according to arrangement of the periodic table. The first one is that the elements are arranged according to groups. And each group is, each column corresponds to a group. As I've mentioned, that these are the ones, group 1, group 2, 3, 4, 5, 6, 7, and 8. And again, we've put aside the transition metals for now. And then the second interesting fact is that actually the group number an element belongs to tells us of the number of electrons in the outer shell. Why are we interested in electrons that are in the outer shell of an atom? The truth is, only these electrons, the electrons in the outer shell, are the only ones that participate in bonds or reactions. Whenever an element bonds with another, whenever an atom bonds with another, the only electrons responsible for that bond are the outer shell electrons. The shells that are in the inner shell do not participate in bonding, only the ones in the outer shell. So the group number tells us of the electrons that are available to make bonds. For instance, over here, we have group 1. All these atoms belonging to group 1 tells us that each of these elements has one outer shell electron. In other words, there's only one electron available to make bonds. The same goes for this group. All these elements belonging to this group have 2 electrons that are available to make bonds. Over here we have 3 available to make bonds, 4 available, 5 available, 6 available, and 7 available. The last group is quite unique because of a fact which we will mention later. Okay, so that was fact number 2. And finally, well, not quite finally, but almost toward the end, the main point is that elements in nature are more stable when they have 2 or 8 electrons in the outer shell. That's the only time that typically, in the natural sense, that is what we find in nature, is that elements are more stable when they have 2 or 8 electrons in their outer shell. Many of these atoms, if they have more than 2, they will take the easiest way to acquire the state of either having 2 or 8. What do I mean by that? For instance, let's take lithium. Lithium has 1 outer shell electron, which means it will be stable if it has 2 or 8. If we were to try to get it to have 8 outer shell electrons, that means we would need to supply a total of 7. Because it has 1, we would need to supply 7. That's one way to make it stable. Or the other way is to just supply 1 extra electron so that this lithium would have 2 outer shell electrons. So instead of lithium seeking bonds that would supply it with 7 electrons, it would typically, we would most commonly find it in bonding with other atoms that provided just with 1. So this guy is likely to make bonds with things that would get it to have 2 outer shell electrons. Okay. The other side is true also. Let's take, for instance, let's take chlorine. Chlorine is in the group 7, which means chlorine has, it's just shy of 1 electron to acquire a total of 8 outer shell electrons. So chlorine is likely to make bonds with other atoms which will supply it with the 1. It is more likely to take electrons from other materials than to give up its existing 7, because that would be more effort. This is what I mean by elements will take the easiest way of acquiring the state of having 2 or 8 electrons. If 2 is easier, it would take this route. If 8 is easier, it will take that route. Okay. And actually, this little principle here is a reason why certain bonds are natural in nature. An example of this is water. If you consider hydrogen is in group 1, which means hydrogen needs just one extra electron in order to gain the status of having 2 outer electrons. Notice oxygen, on the other hand, belongs to group 6, which means it needs 2 more electrons. If it were to acquire 2 more electrons, it would get to have 8 total. So hydrogen is happy to have 2 electrons because that's the easiest way it can get to that state. It could either go to having 2 electrons on the outer shell or 8. Well, the shortcut is to just get to have 2 electrons, in which case you just get 1 extra, whilst oxygen needs 2. This is why when you have an oxygen atom in water, you have 2 hydrogens. It's because this 1 hydrogen provides the 1 electron to the oxygen, and the other hydrogen provides the second electron, fulfilling the 8 electrons which the oxygen needs. But notice, oxygen also provides 1 electron to each hydrogen. So both of them are happy. So both the hydrogen acquires its state of having 2 electrons, and oxygen acquires its state of having 8 electrons. And this is why water is very stable naturally. By the way, this kind of a representation is called a Lewis diagram or a Lewis structure. It's very helpful when you want to signify the most important aspects of bonding. It highlights the electrons that take part in bonding. The green dots here correspond to electrons that are covalently bonded to the oxygen and the hydrogens. So, again, oxygen has 6 electrons in its outermost shell. And look, 1, 2, 3, 4, 5, 6. That's what this Lewis diagram shows us. It doesn't highlight all the electrons that oxygen has, but only the ones that participate in bonding, and those ones are the ones that in the outer shell, which coincidentally is equal to the group number. Okay, and hydrogen is in group 1. It only has 1 electron which takes part in bonding. That's why next to the hydrogen we have 1 dot, and the same goes there. But because these electrons are shared, so they essentially belong, this is covalent bonding where electrons are shared in the bond. It's not like ionic bonding where the electrons are completely removed. Okay, let's consider another example. This example is silicon. Silicon, if we go back to our group of our table of elements, periodic table of elements, you'll notice silicon is over here. It has 14 total electrons, but notice it's in group 4, which means only 4 of those 14 electrons are available to make bonds. So if you have a large sample of silicon, pure silicon, we know that those silicon molecules are bonded, or those silicon atoms are bonded through those 4 outer shell electrons. What does this look like? Let's use the Lewis structure. So silicon over here has 4 outer shell electrons, so each atom is going to have 1, 2, 3, 4. 1, 2, 3, 4. Outer shell electrons 1, 2, 3, 4. 1, 2, 3, 4, and so on and so on. But notice, over here, let's consider this atom. This atom has its outer shell, in its outer shell, because of the covalent bonding, it has 4 outer shell electrons, but because it's bonded with the surrounding electrons, it not only has these 4, but the ones that it has shared. So the 4 from that it has from it by itself, but it shares this one, that one, that one, and that one. So 4 from itself and 4 from sharing. So this atom here has a total of 8 outer shell electrons, which means this guy is going to be stable. Because the outer shell has 8 electrons, this means this silicone is not going to be willing to allow electricity to pass, because all of these electrons are occupied. They are paired up. There's none available to move, to conduct electricity. Actually, another way of stating this is that the outer shell of this sample is completely filled, because each atom here has 8 electrons belonging to it. Of course, 8 electrons through the covalent bonding. So no electrons available. Its outer shell its valence shell is completely filled, which means its conduction band is empty. Hence, silicone is an insulator. Quite shocking. It is an insulator. Let's do something interesting though. Let's target this atom and swap it out for something else. Let's consider, for instance, arsenic. Arsenic is an element which is in group 5, which means it has 5 electrons available for bonding. Now, if we were to replace that silicone with arsenic here, we know arsenic is going to have 4 electrons, which are going to be bonded with the 4 surrounding silicones. But then arsenic had 5. So 4 are going to be bonded, but the 5th one is going to be roaming. The 5th electron, which comes from the arsenic, is going to be available to conduct electricity, which means this electron will have to live in the conduction band, because all these ones have 8 electrons, which means that the valence band is going to be completely full. So there will be no room for this electron to reside in the valence band, so it would need to be promoted or moved to the conduction band. And because it will be in the conduction band, this substance, this silicone, which has arsenic in one of these edges, in one of these sides, will be a conductor, because it will have available electrons. Now, because arsenic introduced an extra electron, this type of conductor, of course, this is essentially, I shouldn't say a conductor, it's a semiconductor. Because of our introduction of arsenic, we ended up with an extra electron, which is available to conduct electricity. This type of semiconductor is called an N-type semiconductor, because it introduced a free negatively charged particle, negative electron. So we call it an N-type semiconductor. So this type of semiconductor, silicon arsenic, is an N-type conductor. This is typically true when you introduce a foreign particle or a foreign atom which has more valence electron or outer shell electrons than the substance in question. So notice arsenic has 5 extra electrons, or 5 outer shell electrons, while silicon has 4. So by replacing one of the silicons and with an arsenic atom, we're going to end up with a free roaming electron. Essentially, we have designed, or we have made, what we call an N-type semiconductor. What happens if we had introduced a foreign particle or a foreign atom which had a less number or a lower number of outer shell electrons than the host substance? In our case it's silicon. Let's consider a very simple one. This is aluminium. Aluminium has 3 outer shell electrons. In the periodic table, it resides in the third group, third column, which means if we're to replace the silicon, which was on this site, with aluminium, what we're going to end up with is we're going to have the electrons 1, 2, 3, but we will be missing a 4th one with which it can bond, so that the aluminium has 8 electrons surrounding it for it to be stable. The point is, aluminium will have a shortage of an electron here. This shortage of an electron is going to leave this site positively charged because we have a shortage of electrons. Essentially, we call this lack of this missing electron, we call it an electron hole. Sometimes people just say hole. This hole is actually a vacancy which other electrons can fill in. When the other electrons make a jump into this hole, wherever they came from, they leave a hole behind. And by the electrons filling in these holes, actually, they essentially conduct electricity. Actually, here we call it the hole. As electrons move to the hole moves away from that site. For instance, let me use this as an example. For instance, if we had an electron here, maybe change color, let's use blue. Let's suppose we had an electron here, residing somewhere here. When this electron observes this hole, because this hole is positively charged, when this electron gets attracted here, it will move and take away this charge. It will move this to this region. But then, what will it leave behind? What would remain where it was? Well, what will remain where this electron was is going to be a hole. There's going to be a gap. Again, the positive charge. As the electron moves this way, the hole is going to move the other way. This type of substance, because of our introduction of aluminium in this substance, we have produced a hole which is positively charged because it lacks electrons, it's short of electrons. This type of semiconductor is what we call a p-type semiconductor. P because the hole is positively charged. Another way of saying it is that what carries electricity through here is through the hole, the empty hole, the lack of electrons. That positively charged hole is the carrier here. So this type of a semiconductor is called a p-type semiconductor. Let's put it all in summary now. Notice we have taken a substance which was an insulator which had no desire of conducting electricity, and we have introduced a foreign substance which in this case was aluminum, and over here was arsenic. We have introduced this new substance, and as a result, the combination of these two substances is now able to conduct electricity. So the conditions are favorable for this substance to behave as a conductor. So we have a semiconductor by introducing these foreign substances. These foreign substances are called impurities. We started off with the pure silicon, and we replaced one of the sites of one of the silicones in one of the sites with aluminum, so that aluminum is going to be an impurity. And the act of replacing the silicone with an impurity is called doping. You are doping the sample of silicone with an impurity. Now, depending on what kind of carrier the impurity produces, that dictates the kind of semiconductor we obtain. When the impurity produces excess electrons, in other words, by introducing this impurity, we end up with extra electrons, that type of semiconductor produced by that kind of doping is going to be called an N-type semiconductor. Example of this was arsenic. When we introduced arsenic, because arsenic had 5 electrons, we ended up with an extra floating electron. This extra electron was available to carry electricity through, to conduct electricity. So this type of semiconductor is an N-type. The other side is when the impurity produces holes, that is, there's a shortage of electrons. Because of the shortage of electrons, there's going to be a net positive charge on the site of the impurity. Essentially, this will make our semiconductor a P-type because of that positively charged hole. This is how we produce semiconductors through the process of doping. Actually, our diodes, the semiconductor, you might remember in rectification, we use diodes. Actually, diodes use this exact, they use these semiconductors in order to make diodes. When you apply electricity one way, it fosters the flow of current. When you apply electricity in an opposite direction, you reverse the polarity. That would hinder the flow of current. That has to do with the type of semiconductors on your diode. Okay, with that much, I will pause here and we'll see you in the next video where we will begin to talk about how these ideas of semiconductor physics are applied in semiconductor devices, like I alluded to with the diode, and also we will talk about how these ideas are also used in radiation detectors. I will stop here. See you in the next one.